Recording. All right. Yes, you don't have to do it today. Just do it this week. So here's the procedure. First, using the auto tune. So when you auto tune, you will have a P, I, and D. And the P, in my case, I'm not sure you guys, auto tune was supposed to finish last week. So I hope everybody already did the auto tune. So the proportional band is 200, is about 200. And the integral time is about 150 seconds. This band, there's no unit, it's just percent, 200%. So that's the band. Generally, we do not see the percent, we just see 200. The band is 200. So after the auto tuning, the proportional band is 200. Integral time is 150 seconds. And the derivative time is about 50 seconds. So that's about the result of auto tune. So if your result is different from mine, doesn't matter. So just use mine as the example. PID controller count for 95% of industrial control applications. So almost all the industrial control, process control is done by PID. There are many reasons. One reason is very easy tune. The tuning is relatively easy. And it's also very tolerant. So if your parameter is off for the optimum, you still get very good results. So easy tuning means you do not have to have a perfect tuning. In a very large range of tuning, you all get very good results. It may not be the optimum results. If you want the best performance, you might spend a little bit of time. But to get good results, PID tuning is relatively easy. So here's my results from a computer. So the first experiment we're going to do is called P proportion only. So what do we mean proportional only? That means we will use my auto-tuning result as a starting point. We will do proportional band, P band equal to 200. I want the integral to be 0. Well, integral to be 0 means integral time equal to 9,999. You don't have to go all the way to 9,999 because it takes a while to increase that number all the way seconds. Anywhere to, for example, 2,000 or 1,000 is enough because the tuning is 150 seconds. That's the right timing. So if you make it 10 times longer, it's basically reduce it to 0. So I want the larger this number, the larger the integral number, the smaller the integral effects. Let's make. And so that means 0. 0 integral. Derivative time equal to 0. That means 0. So derivative, if you put 0, that means no derivative. So we put a very large integral time. We put 0 derivative time. And then you turn on the controller, put the set point about 1 or 2 degrees above your room temperature. So the set point is plus 2 degrees. Whatever room temperature was, plus 2 degrees. That's so if your room temperature, for example, right now is 65 or 68. If your room temperature is 68, you just put the set point 70. So then you watch the controller to do its thing. So after I will use a cell phone or use a digital watch as a timer. I will record the timing. So this is the time. Horizontal will be time. Vertical will be temperature. So this is where I start, 68 degree, and this is where I want to end, 70 degree. And you notice that your controller will do something like this. So that's where you turn on. You start at here. It has a long delay. After a long delay, so you will record your temperature, for example, every 10 seconds. You write it down, take a pen, write down the temperature every 10 seconds, and then you plot it. 0 seconds, 10 seconds, 20 seconds. About 1 or 2 minutes, mine is very slow, so the delay is quite significant. About 1 minute of delay, 60 seconds, the temperature starts to rise. And that's 70 degrees. You noticed the temperature will never reach 70 degrees. That is what it is. Proportional only have a steady state error. The steady state error is the problem with a proportional controller. So what is the steady state error? That is steady state error. So your controller the temperature will reach, for example, 69.5 degree. And there is just this 5 degree error. No matter how long you wait, you can wait a day, you can wait an hour. This half degree error is always there. Why? Because if there's no error, let's assume there's no error. Then there is no correction. That means your light bulb will not be turned on because it's proportional only. So if there is no error, your light bulb or your heater will be turned off. What happens your heater turned off? You get cold, right? So in order to turn it on, you always have to have an error for that heater to be turned on. That error is called the steady state error. So that's the first experiment. The second experiment, we will use a PI control. To use the PI control, we add the integral time 150 seconds, proportional band 200, derivative 0. So that's our second experiment. Proportional, integral, and the derivative. Derivative will be 0. So now, because the integral is introduced, it will completely eliminate no SSE. So that is the function of an integral control. It will completely eliminate SSE. So what happens is if you watch the controller, you set it another 2 degrees above, set point is another 2 degrees. Whatever your controller right now, for example, right now is 70 degrees, you set it to 72 degrees. So you started with 68 degrees, but after a while it gets warmer, and you put it set point another 2 degrees above your current incubator's temperature. So when you look at that, you will see 70 degrees, and this time the delay may be not as long because when you get started, the light bulb is cold. Now the light bulb is almost lukewarm. So there is also a delay, but the delay is not as significant. But you will notice It will reach 72 degrees perfectly. There is no steady state error. There is a delay, and the temperature will rise, and you will record the temperature. So this is 10 seconds, 20 seconds, 30 seconds, whatever. After 5 minutes, it reaches a perfect temperature. So you will take a measure temperature, and then you will make a plot 1, plot 2. So what you need to do is you take a picture of your 2 plot. You can plot it with hand, just like I did here. And after you have the 2 plot, you upload it to Canvas. I will put an assignment after this class. I will have an assignment on the Canvas. The third plot, the last plot, is the PID control. PID control. PID control, we will put a derivative to 50 seconds. So what will that 50 seconds of derivative will do to our controller? It will increase the response time of our controller. So what happens is the controller will respond faster. Controller will respond faster. So what we will do is, in order to show the controller can respond faster, we will put the proportional band to, we will half it. That means we will double the band. 100, we will double the band. Integral will be remain the same, 150 seconds. So now, the third experiment, we were trying to get performance. So we will double the band, double the gain, half the band. When we half the band, we means double the gain. So the proportional gain will be doubled. And now your set point will be now 74 degrees, another 2 degrees above. Why our set point keep going up? The reason is our controller can only heat, cannot cool the incubator. So you have to wait a relatively long time for it to cool down. Alternatively, you can blow some cold air into your little incubator. But otherwise, you just put the set point another 2 degrees above. And now you will observe the performance of your controller. So this is the temperature, this is time, and this is 72 degrees, that's where you started. And this is 74 degrees, that is where you want to end. And you will notice faster. So this curve go up faster instead of like this previously. Why we go faster? Because the proportional gain is doubled. We double the gain. When we double the gain, we have a faster response. So the temperature will rise faster speed. And then you will record the response. So you will record, for example, the 10 seconds, 20 seconds, 30 seconds. And you will compare your third results to your second results. And then you compare your second results to the first results. So what's the difference? Let me summarize. The difference of P controller is SSE. You have SSE. SSE. So SSE is cannot be eliminated. You always have SSE for proportional controller. So that problem can be eliminated by integral. So we have 150 seconds integral control that will completely eliminate. Then we have a derivative. Derivative will provide the performance increase. So with the derivative, you can increase the gain of your proportional controller. By increase the gain of your proportional controller, you will speed up the response of your PID controller. So the PID altogether generally will have the best performance for your process control. So once you understand what the proportional will do, what the integral will do, and what the derivative will do, then it will that will be very good experience. And then potentially you can apply a job. You can finish tuning an industrial PID controller, because 95% of the controllers are PID controllers in the industry. So again, it's relatively easy tuning if you have a little bit of experience. So with a little bit of experience, the PID controller is relatively easy tuning. And also, it's very tolerant. So, for example, if you change this to 150, still have very good performance. The performance will be different, but you can change that to 100 seconds or 200 seconds. Yeah, you can experiment. Derivative. Don't make it too big, because the bigger, the more derivative, the more susceptible to noise. So 50 seconds, whatever time, or put it at 0. In this experiment, the derivative, because we are not looking for that performance, it's not a good performance. Also, the temperature. But we can still experiment with the proportional, so we can find this performance gain right here. How about you keep increase the gain? If you keep increase the gain, you potentially will overcorrect. That means like this. That's an overcorrection. Okay. So that is if the gain is 50. I actually did this last night. I put the proportional band as 50 instead of 200. I changed it to 50. What happens is if I set point is 74, my controller just ran way over 74 up to 76. So it's just completely overcorrected. So that is a potential problem you might have if your proportional gain is too big. In this case, I enter 50 as the band. My band is 50. I did it last night. It doesn't work very well. So in that case, obviously, we never want to put 50 as a proportional band, because it just goes right over. And then the temperature drop is very slow. It will be long time to go back. And after a couple of oscillations, it might ended up with 74, but obviously that's not as good as this. Just reach 74 and stabilize 74. I did a little experiment, a little bit at 100. There is a little bit of overcorrection, like this. Not as significant. There's a little bit like a 0.1, 0.2 degree above, 0.2 above, and then settle down. If you change it to 50, it's not 0.1, 0.2 degree above. It's like a 3 degree above, 2 degree above. So that will be way overcorrect. So that means if you see that happens, that means too much proportional gain. You need to halve it, lower it. So that's so today that's today's lab assignment. I will just end here, and I put the assignment on Canvas, and you guys have 1 week to finish this. All I need is 3 plots. The first plot is a P control. The second plot is a PI control. The third plot will be PID control. Okay.
So how do we set that in our actual equipment again?
Very easy. You go to the. I can demo it, but you can read the little menu, the one-page menu.
Yeah, I figured. Okay.
Yeah, you go to you press set for 3 seconds, and after 3 seconds you enter a menu, and then you go to the PID menu. The PID menu, you go into PID menu. You can change the P, you can change the I, you can change the D. You can change each separately.
Right.
PID, yeah. After self-tuning, I would like to ask you guys, anybody did the self-tuning?
I did the self-tuning.
I did it.
Okay, tell me your proportional band. What is your proportional band?
146.
146. How about you, Joe?
Hang on, right here. 471.
471. Oh, we have a wider range. 471 is very low gain. That means your heater is very powerful. I would assume your heater is so hot. And I was thinking Tim's heater is a little weaker than mine. I don't know. Maybe Tim's box is too big. Yeah, maybe Joe has a small shoebox.
It is. It's a pretty small one. It's also getting about 40 degrees of temperature range.
Wow, that means that's another reason that's another proof your heater is very powerful. Yeah, 40-degree range. Wow.
Now, when you do the auto tune, you're supposed to set it at the maximum temperature you're going to reach, right?
Yeah, the computer will just don't care about your setting. The computer will just turn on the heater and look for patterns. The set point doesn't care. Anybody else? How about the derivative integral? What's your integral time, Joe?
59.
59. How about
259.
259. Okay. How about Tim?
78.
78. Okay. So yeah. How about derivative?
64.
54.
64.
64. Okay.
Mine was 19.
19. So Tim has a very small derivative, has a very high integral. Oh, I have very high integral and high proportional compared with mine. Joe has a small proportional because the band is almost 500. That means the gain is very slow. Very small integral also. And the big derivative, because your controller is so powerful, the derivative means braking and boost. So when your controller is controlling too fast, derivative will break your controller. Will be the braking action. It's just like you are parking your boat. When you are far away from your target, you accelerate your boat. When you almost reach your target, you brake your boat. Because if you don't brake your boat will crash. The derivative will have if you have a lot of error, that means your heater is not powerful. The derivative will provide a boost. But if your heater is so powerful, you're reaching target so fast, you almost crashed. The derivative will break. Will break your output. So. Okay, anybody else did the auto tune besides Joe and Tim? That was last week's assignment. I didn't put a. Okay, looks like we only have 2. Anyway, if you don't do it this week. So number 1 procedure will be auto tune. So after the auto tune, you use the auto tune as the base. So if Joe is working on the step number 2, Joe will put 450 here, 470 here instead of 200. So depending on the result of your auto tune, you will change numbers here. So for Tim, you will put 150 here. For Joe, will be 550 here, 450 here. So you do your test based on your results. the auto-tune result is based on a lot of factors. Like I said, the size of your incubator, the power of your heater. Yeah. Okay, anybody else have comments?
Oh, wait.
Oh.
Explain that again. So we do the auto tune, and then we take those values and we change them accordingly.
Yeah, you'll change them accordingly. Yes, perfect.
Okay. Awesome.
All right. More questions before I close?
I just want to show you my box since I didn't do it last week.
Okay, show us your box. Arturo, show us your box. Mine. Your box is looking good. How about inside? Yes. Okay. Perfect. How about your heater? Show us your heater. What kind of heater are you using?
I believe it's a 60-watt bulb.
It's both. Okay, it's almost identical with mine. So the size is almost identical with mine. So I would expect your auto-tune result will be also similar to mine.
Probably. Once I get it done, we'll know for sure.
All right. Okay.
I had a tough time finding, good concrete directions on the auto tune. I probably did it 6 times over the weekend.
Okay. Let me show you a PDF document. That is how the auto tune is done by. Let me show you a PDF document. Excellent question. Let me show you. I would that will be the topic next week. Next week we will do a auto tune tuning lecture. But you asked. Let me show you this. If I can find it, where is I don't know where I put that file. We will talk about next week, Joe. How about that?
Okay.
There are many ways to tune, and the auto tune is just to put that method into a computer code.
And mine took a long time. Sometimes I left it overnight a couple of times trying to get it to resolve itself.
Oh, okay.
But that might just be because I got that weird heating element.
Yeah, I see some report says this PID controller may have bugs. I don't know. So we have to trust the manufacturer who coded their controller perfectly. They may have bugs. I don't know. But so far so good for our little experiment. But in some extreme case, they might behave strangely. Yeah. Anyway, it's a $25 controller. So. All right, excellent. If we don't have questions, because I like to record the questions also, because your question, most likely others have similar questions. So for those of yeah, continue. Yeah.
One more question.
Okay.
Will we be able to contact you this weekend if we have any problems?
Oh yeah, that's a very good question. Send me an email. I will most likely the best chance to get hold of me is the email. Then we can make arrangements on the time or something, Zoom meeting.
Awesome. That's good. Thank you.
Very good question. Yes. Yeah. You see, everybody had the same question. It's just you asked. Or you,
Actually, I do have a question. For next Wednesday, will we also have a lab or an assignment?
yes. Next Wednesday we will do a tuning, manual tuning.
Okay.
We will, because next Monday we will study how to tune, the tuning method, and Wednesday we will practice. We will do a little bit of practice. We will use one most popular tuning method, trial and proven method, 50-year-old method. That's how I'll tell you how proven it is.
Okay.
All right. See you guys next week,
See ya.
and have a good weekend.
See ya.
Two.